Good morning, ladies and gentlemen, and welcome to our OI Analytical webinar. My name is Michael Watt, and I'll be coordinating the webinar for today. At this time, I'd like to introduce our guest speaker, Dr. John Welsh, who is the OI Analytical TOC Product Manager. He's based in our Texas office, and he's been with OI Analytical for 18 years, a man of much experience. John, thank you very much for coming on today.
Oh, you're quite welcome, Michael.
What time is it there in Texas?
It is just a little bit after 8 o'clock in the evening.
8 p.m.
Perfect time for a webinar.
Perfect time. Yes, and thank you very much for giving your time at that hour. And just a reminder to our audience, there will be a question and answer period at the end of the webinar. However, you are free to type in your questions at any time during the webinar using the chat question box on your interface, on your GoToWebinar interface. And I'll let you take it away.
Thank you, Michael. Yeah, once again, thanks to Michael and Ramiko for organizing the webinar. I'd like to welcome our guests and extend my wishes to you for your health and safety in these trying times. I'm pleased to report that on my end, myself and my family are safe and well from the coronavirus. In addition, although we have not officially planned it, we do plan to have an ongoing series of webinars on various TOC topics, and I will extend my invitation to those on this webinar for webinars in the future when they are announced. So with any further ado, let's get started. In today's webinar, I will be covering the importance of TOC, oxidation techniques and the history of TOC as an analytical technique, the fundamentals of TOC, description of TOC techniques, and the applications and limitations of those TOC techniques. Hopefully, this webinar will provide you with a greater insight into the TOC techniques that are available today and assist you in the decision-making process as to which of these techniques is right for your particular application. The importance of TOC as a water quality parameter cannot be understated. Generally speaking, when we think of contamination in water, that contamination is comprised of carbon-containing compounds. This is true for all applications. Ultra-pure water for microelectronics fabrication, boiler feed or process water, water for injection, and clean-in-place validation in the pharmaceutical industry, as well as drinking water and wastewater. So while the picture that you see before you here represents an idyllic setting, whether or not that water is contaminated is a question. While it looks very beautiful, it could be contaminated with some type of organic containing compound. TOC determination provides quick and easy indication of organic contamination. It can be used as a general screening tool and indicate if predetermined acceptance criteria are met for a wide variety of applications and processes. As we will see in the history of TOC, the need for total organic carbon analysis grew out of the need to monitor seawater. In my experience, I've seen that the genesis of TOC started with a lot of oceanographers. Today, TOC is used for compliance monitoring to protect water quality and establish criteria for screening and measuring contaminant levels. TOC is used by service contract laboratories and municipalities for the analysis of a wide variety of samples. The United States Pharmacopoeia, European Pharmacopoeia, Japanese Pharmacopoeia all mandate TOC analysis as a required test. In emerging markets, such as those in your area in Southeast Asia and China, these practices are being adopted. For process control, a predetermined level of TOC has been defined, whether that be wastewater effluent from a chemical or petrochemical plant, or ultra pure water for injection in the pharmaceutical industry. In those applications, TOC determination provides valuable insight into the proper functioning of that process. Strictly speaking, it is important to note that TOC is not a regulated parameter. For instance, as a permit requirement in the operation of a water or wastewater treatment plant. However, there are agencies and congressional acts in the United States that have set regulations on TOC or other contaminants that are directly affected by TOC concentration. And I'm sure the same or equivalent agencies are represented in your countries as well too. The Safe Water Drinking Act sets limits on disinfection byproducts that result from the disinfection of drinking water. The trihalomethanes and haloacetic acids generated in the disinfection process are directly correlated to TOC concentration. The National Pollution Discharge Elimination System mandates BOD, COD determination as a permit requirement in wastewater plants. TOC can be used as an estimate of BOD, COD after a proper correlation study and determination of a correlation factor. The Resource Conservation and Recovery Act requires operators of waste disposal sites to monitor their groundwater quarterly basis for organic carbon and organic halide levels. I will cover briefly the oxidation techniques that give name to the TOC analyzers that are available today. In addition to being a chemist, I have a keen interest in history. And as such, it's interesting to note how the evolution of TOC technique came about and the history of it. The evolution of various oxidation techniques can be understood if we study the history of TOC. In the 1630s, Flemish scientist Jean-Baptiste von Helmont identified the gas emitting by the burning of wood as carbon dioxide. In 1756, Joseph Black demonstrated that carbon dioxide occurred in natural air and could be created from other compounds. While doing research on magnesium carbonates, Black invented the analytical balance and used it to measure carbon dioxide by loss of ignition. The Loi Test, in which samples are heated and reduction in mass is measured, is the first quantitative test for carbon. Organic matter in soil has traditionally been measured by LOI or chemical oxidation using dichromate solution. The dichromate present as hexavalent chromium reacts with reducing organic carbon in strong acid solution to form trivalent chromium. Titration of the unused hexavalent chromium with ferrous iron yields a method capable of estimating the organic carbon present in the sample. That's the genesis of COD. A steel or coal sample can be placed in a furnace or heated tube, and in the presence of oxygen, the carbon converts to carbon dioxide. The carbon dioxide can be collected and measured, or it can be determined by a carbon dioxide specific detector. The initial steel analysis apparatus provides a basis for the modern TOC analyzer. In 1924, T.D. Jensen of the Westinghouse Electric and Manufacturing Company patented a measuring device that placed steel samples in a horizontal 1,000-degree furnace that combusted carbon in an oxygen carrier gas and collected CO2 cryogenically. In 1948, American Cyanamid patented an infrared or an IR analyzer. Frustrated with an inability to achieve lower levels of detection on seawater using existing TOC combustion analyzers, recall that Thiel's analyzer had a lower limit of detection of 2 milligrams per liter, Menzel and Vaccaro devised an ampule-based wet chemical oxidation technique based on earlier work by R.F. Wilson. Wilson digested seawater samples using sodium persulfate at 100 degrees C. Menzel and Vaccaro's ampule method allowed for simultaneous processing of a large number of samples. In 1965, Alan Fredericks and Donald W. Wood developed a TOC method based on Menzel and Vaccaro's ampule method that determined TOC in seawater using gas chromatography. The gas chromatographic method was later adapted to use an IR detector, and the newly formed company, Oceanographic Institute Corporation, OIC, or today as it's known as OI Analytical, commercialized the instrument. This new TOC analyzer digested samples using Prosulfate chemical oxidation by autoclaving samples enclosed in these ampules. An autosampler broke the ampule and swept CO2 gas into an IR detector. This instrument was capable of analyzing carbon in seawater to as low as 0.2 milligrams per liter. The ampules had a significant advantage in that samples could be collected and sealed at sea pending subsequent digestion and analysis on land. In 1967, James Teal at Dow Chemical Company patented a method and apparatus for determination of total carbon content in aqueous systems. This apparatus is a combustion system that is similar to Jensen's device and manually injects aqueous samples directly using a syringe into a stream of oxygen, flowing through at 700 to 900 degrees C furnace, measuring the CO2 generated with infrared absorbance. The patent states that previously accepted methods for the determination of carbon in water were based on chemical oxidation methods at moderate temperatures. Teal's device appears to be the first combustion TOC analyzer for water, and the previous method he is referring to is likely the chemical oxygen demand test. The method reported an analytical range of 2 to 500 parts per million and 98% or better combustion efficiency for all organic compounds tested. In 1969, Earhart developed a TOC method using a Technicon auto analyzer. This method combined continuous flow, ultraviolet irradiation, and persulfate oxidation and collected the CO2 generated into a dilute sodium hydroxide solution, measuring carbon by a change in conductivity. In 1984, Cowett improved on Earhart's original procedure by optimizing pH, persulfate concentration, UV, and IR detection. And finally, in 1988, Sugimura and Suzuki reported on a high temperature catalytic oxidation, an HTCO method as we refer to them, for the analysis of seawater by direct injection of 200 microliters of sample into a 680 degree C furnace containing a platinum catalyst. The method was rapid and precise and allowed shipboard analysis. Moreover, it demonstrated higher TOC levels in seawater than previous method, namely Menzel and Vaccaro's method, spurring a debate on whether there is undetected carbon by chemical oxidation or whether the HTCO method produces erroneously high results. After much research, it was determined that both arguments were very valid. Initial results generated by HTCO did not properly compensate for high blanks caused by carbon buildup within the combustion tube. However, even when compensating for blank values, the HTCO results were still slightly higher. Humic acids, bacteria, vegetation, and certain high molecular weight molecules are oxidized with greater efficiency using high temperature combustion. The higher oxidation efficiency of high temperature combustion loses its value at low concentrations, below approximately 1 milligram per liter of carbon, since HTCO is limited in sample volume compared to chemical oxidation. So that long history, which I just explained, brings us today to the three techniques that are available for the laboratory. Primarily, these are high temperature catalytic oxidation, heated persulfate with NDIR detection, and UV Prosulfate with either NDIR detection or conductivity membrane detection. Those are the three basic techniques that are available to the laboratory today. So with that said, let me just briefly cover the fundamentals of TOC determination and TOC analyzers. Every TOC analyzer is comprised of these four building blocks. Sample introduction. There must be some mechanism for getting the sample into the analyzer. Some instruments employ direct syringe injection, for instance, direct sample injection into a combustion furnace. Oxidation. Simply put, every TOC analyzer oxidizes carbon to carbon dioxide. There are three primary methods for this oxidation: high temperature catalytic oxidation, heated persulfate, and UV persulfate. That carbon dioxide, which is generated in the oxidation step, is measured by one of three types of detectors: non-dispersive infrared, conductivity, or membrane conductivity. And lastly, there must be some mechanism for displaying, recording, transmitting the data that's generated. In modern instrumentation, that's either an onboard or remote computer. Every TOC analyzer on the market today does exactly these four steps without exception. So what can you measure? In the terms that we use in TOC analysis, we have total carbon, which is the sum of all carbon in a sample and is comprised of three distinct fractions: inorganic carbon, organic carbon, and volatile or purgeable organic carbon. Therefore, when properly configured, all TOC analyzers can measure total carbon. In some instances, some analyzers must measure total carbon as part of the measurement, and I'll discuss that point later. Total organic carbon is the organic fraction of the sample. Determination of TOC requires some mechanism other than just the use of reagents to affect oxidation of carbon dioxide. And lastly, inorganic carbon, or TIC, determination, on the other hand, only requires the use of a strong acid for conversion to carbon dioxide. In the determination of TOC, we have two choices when it comes to TIC: either measure it or remove it from the sample prior to the determination of TOC. NTOC is the organic fraction of the sample that is left in solution after acidification and subsequent removal of TIC from the sample. Today, this is by far one of the most widely used techniques. NPOC is equivalent to TOC when the volatile fraction of that sample is negligible. And in most cases where TOC determination is required, in most application, this is usually the case. Purgeable organic carbon, or POC, is the volatile fraction of the sample that can be removed from solution by simply sparging an inert gas through the sample. Determination of POC does require special apparatus on TOC analyzers. As previously stated, it's usually negligible or of no concern in TOC determination. If I had a sample which I thought was very high in purgeable organic carbon and that was of interest to me, I would probably move to a different technique that's more amenable for both the quantitation and the speciation of whatever those volatile organic compounds are. And finally, dissolved organic carbon, by regulatory definition, is the measure of TOC or NPOC after filtration through a 0.45 micron filter. So as far as analysis modes goes, there's two directly available on a TOC analyzer. In non-purgeable organic carbon, the sample is acidified and the carbon dioxide from the acidification of the TIC fraction is either measured or vented out of the reaction chamber. For combustion TOC, an aliquot of this acidified sample is injected into the combustion furnace. For heated persulfate TOC, Prosulfate is added to the acidified sample, heated to 98 degrees C, and reacted for a preset amount of time. For UV Prosulfate TOC, Prosulfate is added to the acidified sample and the mixture is irradiated with UV light, again, for some preset time. And TOC by subtraction, as the name implies, requires two measurements for the measurement of TOC. First, the total organic carbon, or TC, is determined. For combustion TOC, a sample aliquot is injected directly into the combustion tube. For heated Prosulfate and UV Prosulfate, the reagents are added together in one step. Heat is applied for heated Prosulfate, UV light for UV Prosulfate. Next, the total inorganic carbon is determined. On all three of these techniques, this simply involves the addition of acid to a sample aliquot and the measurement of the resulting carbon dioxide. Subtract the TIC value from the TC value, and you have the determination of TOC. Very quickly, I am a chemist by profession, and I would be amiss if I did not include some very simple chemistry that goes on in the analysis of samples and the determination of TOC. For the removal or determination of TIC, acidification is required. There are no exceptions to that. All aqueous samples, even high purity water, will contain some inorganic carbon. Bicarbonate ion is converted to carbon dioxide. Bicarbonate predominates in water with pH on the level of 4.5 to 8.3. Carbonate ion is converted to carbon dioxide, and carbonate will predominate in very alkaline waters. All TOC methods operate by oxidizing organic carbon to carbon dioxide. Some older methods measure the loss of oxidants, such as in a dichromate method. However, for a more accurate measurement of carbon, the CO2 generated should be measured. And it's a very simple equation, as you see here. There is some type of oxidant which converts that organic carbon to CO2. And this chart shows the typical values of organic and inorganic carbon in various types of waters that could be analyzed on a TOC. This chart also provides the information that can be used in the first step in the determination of which TOC technique may be appropriate for your application. Not every TOC technique is applicable or recommended for all of these applications. And further information or material that's available to you can be found in the regulatory methods. I put a lot of emphasis on the information that's available in regulatory methods, as they provide guidance on what is capable or what each technique is capable of doing. And while this slide may not be completely exhaustive list, I do show the most relevant methods that are on the books today. I will only touch on a couple of them. I highly recommend that analysts and other stakeholders take the time to become familiar with the methods that pertain to the various TOC techniques or to the TOC technique that you may be using. While a lot of these are specific to US EPA, in general, I have found that in other countries of the world, a lot of the methods that come from the United States are used as the basis for measurements in various countries. And in some instances, they're practically identical. And remember that these methods provide guidance. They are not rules. They are available to help the laboratory achieve good results for proof of compliance to a third party. The importance of the methods is that they provide guidance on which TOC technique may be best suited for your application. And like all regulatory methods and regulatory bodies, they tell us what to do. They just don't tell us how to do it. That's what these methods are for, is to give guidance on the how to do that. It is in these various methods that we start to find guidance on which TOC technique is most applicable to your application. For instance, EPA 415.3 covers all of the TOC techniques and applies to source and drinking water. Standard method 5310 is probably one of the most widely used methods today. Standard method 5310 covers all three of the TOC techniques. It is then divided into 4 sections, A, B, C, and D. Section B is concerned with combustion TOC, while Section C is concerned with heated and UV Prosulfate. It includes statistical data from ILS studies for the Prosulfate methods, and that statistical data is important in determining a statistical basis or data on which the method was developed. Standard method 5310B offers pertinent information on the combustion TOC technique. While this is not a complete listing of all the recommendations, these are the most salient points about this technique. In general, the combustion TOC technique is applicable when all TOC concentration is above 1 ppm. Another major limitation of the combustion TOC technique is the magnitude and variability of the blank. While the method does offer the choice between phosphoric and sulfuric acid for the TIC removal step, I contend that sulfuric acid should not be used, as this is a potential poison for precious metal catalysts. These are not my opinion or the opinion of OI Analytical. These are statements directly from the methods that give guidance on what's capable on a technique. Standard method 5310C offers pertinent information on the Prosulfate TOC techniques. In general, these techniques are more applicable with low-level TOC samples. However, as indicated, they do have certain limitations for certain samples. However, in most cases, adjustment to the instrument can mitigate some of these limitations. For instance, the use of higher Prosulfate concentration for high chloride samples. Going back to the timeline, we can see that a significant amount of effort was placed on the development of high temperature catalytic oxidation technique. So let's look at some of those characteristics. Dr. Alan Fredericks of OI Analytical was an early pioneer of the combustion TOC technique. Shown here is the model 525 TOC. The combustion tube on the left represents a design that can be found in most HTCO systems on the market today. The combustion tube on the right is unique to the model 1030C from OI Analytical. The principle of the technique is very straightforward. A small aliquota sample is injected onto the catalyst substrate in a combustion tube that is held at 680 to 950 degrees C. This temperature can be higher in some instruments that do not use catalysts. The advantage of using the lower temperature, the 680 degrees C method, is that fusion of dissolved salts is minimized. I'll be covering the topic of analysis of salt in another webinar later on in this series of webinars. Since its inception, not much has changed with the HTCO systems over the years. However, I will present concepts developed by the OI Analytical Model 1080 TOC that are truly unique to the HTCO technique. These are the characteristics of the combustion TOC technique. You can expect higher system blanks due to carbon memory. Certain high molecular weight molecules are oxidized with greater efficiency. As previously stated, at 1 ppm, combustion TOC does lose the high oxidation efficiency. If adjustments to the system blanks can be made, and analysis of samples with TOC values in the 1 ppm range is not a concern, then the combustion TOC technique may be the ideal choice. For low detection levels, a chemical oxidation technique should be chosen. The choice of operating parameters for combustion TOC is relatively straightforward. Of primary concern is the removal or measurement of TIC and the sample volume. Sample volume can vary and is primarily dependent on the calibration range, the capability of the instrument detector, and sample matrix. So we're limited primarily in an HTCO technique by a few parameters that we can adjust in the operation of the instrument. Although the opportunity is there for large sample injection, the preference is for small sample injection size. Impact on the catalyst, particulates, carbon memory should be considered. The effects of carbon memory will be a recurring theme in all of the regulatory methods and is one of the most significant challenges in combustion TOC. All methods vary on TIC removal, and there are several considerations as noted here. It should be incumbent upon the analyst to ensure the removal of TIC under the manufacturer's specifications. Earlier in the presentation, I described how each one of these analysis modes work. One of the most widely used analysis modes is NPOC. However, if your samples contain relatively high concentration of POC, then TOC by subtraction, again, may be the ideal choice. The concentration of TIC relative to the concentration of TOC must be taken into account when choosing the analysis mode. In this example, these are TOC and TIC concentrations that could be found in a typical ground or surface water sample. Within one standard deviation of the mean value, the accuracy of the measurement suffers greatly. And most combustion TOC manufacturers, OI Analytical included, will give guidance on when the ratio of TIC to TOC becomes an important factor in the operation of the instrument. On the other hand, if the TIC is removed from the sample prior to TOC determination and given some statistical considerations, the accuracy of the measurement is greatly improved. So this must be taken into consideration when you're using a combustion technique and dealing with TIC in your sample. There are challenges associated with the combustion TOC technique that are not found in other techniques by virtue of the fact that a combustion tube operating at high temperature is employed in the analysis. At some point, maintenance action on some form or another must be carried out on the combustion tube. This is generally confined to replacement of the catalyst. However, in some cases, complete replacement of the combustion tube may be required. This is particularly true for the analysis of salt-containing samples. In addition to the combustion tube and catalyst, other parts of the system can be affected. This is particularly true for the sample injection system. The Model 1080 TOC incorporates several truly unique and innovative design features. We feel that it will provide very low cost of ownership. Analytically, it exceeds the demands of the regulatory standards, and the intuitive interface reduces operation and training requirements. The Model 1080 TOC incorporates unique design features that help to mitigate the challenges that I just previously mentioned that are faced in the determination of TOC from a wide variety of sources. These include ease of maintenance, smart slide injector, catalyst guard, pulse time injection, stop flow bypass trapping scheme. At some point in time, the catalyst and possibly the combustion tube will require replacement. The Model 1080 provides easy access to these critical components. With the removal of two panels, the furnace and combustion tube are within hand's reach. Operations that generally take hours can easily be accomplished in the matter of minutes. The Model 1080 combustion tube cap uses ramps in the slide to reduce friction while sliding across the sealing surfaces. In our feasibility testing completed during development, this feature increased the lifetime of the sealing O-ring from 30 days to 15 months. The anticipated lifetime of the slide is 18 to 24 months. An off-the-shelf actuator simplifies the design, reduces labor, increases reliability. A quick disconnect linkage detaches the actuator from the cap for ease of maintenance. So what happens in this design is that as this slide moves, sorry, let me go back. It lifts up very briefly, does not lose pressure inside of the cap, thereby reducing the wear on both the slide and on the sealing surface. In the catalyst guard design, a small sacrificial tube is used to protect the main tube and catalyst. The simple feature decreases the frequency of replacing the catalyst and the combustion tube. In our feasibility testing, this feature was tested with high salt particulate samples. So it decreases the cost and frequency of replacing catalyst, reduces startup time after servicing just the guard and the tube. And in our feasibility testing, we tested with high salt particulate samples and verified the cleaning maintenance cycle and quantified extended life of the catalyst. The guard was tested with 3% sodium chloride solution. The Model 1080 ran for over 4,700 injections without failure of the main combustion tube or catalyst. As expected, the guard tube was not reusable. However, it could be replaced and the operation of the instrument continued. For those of you familiar with the OI Model 1030C combustion TOC and the combustion tube previously shown, that combustion tube would clog after approximately 200 injections under the same conditions. This is a picture of the catalyst guard that was in that tube during the test after this high salt test. Clearly, it shows the tube did its job by taking the brunt of the punishment of the salt containing samples. Very quickly, the Model 1080 employs a stop flow bypass injection feature that essentially turns the combustion tube into a carbon dioxide trap. Instead of the sample quickly vaporizing and exiting the combustion tube, valves upstream and downstream of the combustion tube close prior to injection. The longer reaction time mitigates the effects of carbon memory that plague all combustion TOC systems. In conjunction with the stop flow bypass injection feature, the Model 1080 employs what we refer to as pulse time injection. This allows for both large and small sample volumes to be injected more accurately into the furnace. The interval between pulses allows for the carbon in the previous pulse to fully vaporize and react with the catalyst. These are just going to be some typical settings for a 0 to 100 ppm calibration curve. Note the addition of a reaction time for the Model 1080. This is a parameter that is as unique for combustion TOC analyzers because we do allow the sample to react more fully with the catalyst before opening the valves and discharging the CO2 that was generated in reaction to the detector. Sparge time can be kept to 1 minute since the sparge flow rate is 300 milliliters per minute. That would be in the TIC removal step. This is a typical calibration curve for the Model 1080. Note that linearity is well within all applicable method requirements while covering range for a rather wide range of TOC concentration. And lastly, these are some typical results from the calibration curve shown in the previous slide. It's noteworthy to point out that these results were obtained without the use of outlier removal. That is, these are the results from 3 consecutive injections of a standard at each calibration point. And lastly, these are the results from a sequence that was used to validate that previous calibration. This is a typical sequence that might be used in a service contract, municipal, or industrial laboratory. Many times sequences have to be set up according to whatever method the lab is using, particularly if that lab is certified and being validated to a particular method. And this is a typical portion of a sequence that might be set up on the instrument. Okay, going back to our timeline, once again, we move on to other TOC techniques, namely the heated Prosulfate and UV Prosulfate TOC techniques. This new TOC Analyzer digested samples using Prosulfate chemical oxidation by autoclaving samples enclosed in ampules. An autosampler broke the ampule, swept CO2 gas into an IR detector. This instrument was capable of analyzing carbon in seawater to as low as 0.2 milligrams per liter. The ampules had the significant advantage that they could be collected and sealed at sea, pending subsequent digestion analysis on land. Heat is used to optimize the oxidative power of the Prosulfate ion. Prosulfate is a very strong oxidant used in many techniques other than TOC. Prosulfate oxidation is easily adapted to batch analysis and the use of fairly large sample volumes. Unlike UV, heat easily transfers throughout the sample by convection, ensuring adequate contact of organic molecules with the oxidant. There is no need to replace UV lamps or purchase reagent packs. You can purchase needed volumes of acid and Prosulfate or prepare your own reagents, or in our particular instruments, they could be purchased through OI Analytical. Again, very quickly, a bit of chemistry. Oxidation of organic carbon is in heated Prosulfate method is accomplished by the generation of what's known as hydroxyl radicals. This could also be the same mechanism for oxidation in UV Prosulfate technique as well. In the first step, Prosulfate forms hydrogen sulfate ion. In the reaction of water, hydroxyl ions are formed, and further reaction creates the hydroxyl radical. It's that hydroxyl radical right there on that third line that's doing the heavy lifting in the oxidation of organic compounds in these techniques. I'm going to use this diagram from the model 1030W Aurora TOC from OI Analytical. This diagram shows the reaction vessel and heater assembly used by OI 1030W. The heater element at the end of the heater assembly is completely submerged in the sample. The sample, acid, and Prosulfate enter through a side port from the syringe and a multi-port valve. After reaction, water is removed by the condensation vessel portion of the reaction vessel. That would be this portion up in here. Carbon dioxide is swept through a port on the cap of the assembly through a halide scrubber and permeation tube for removal of halides and additional moisture, but they're not shown in this diagram. It's a very simple and effective way to deliver heat to a sample and reagent mixture for the oxidation of carbon. In the combustion technique, inorganic matter that does not combust will build up inside the combustion tube. And this can lead to TOC performance issues and degrade and shorten the life of catalysts. This causes you downtime and is expensive, not only in a replacement, but in time lost. In this heated Prosulfate method, when the solution is drained out of the sample, we take the rinsing volume above where the liquid was for the reaction step and sweep this completely clean. This is one of the features of this particular technique that leads to the lower limits of detection and the cleanliness of the technique as compared to combustion TOC. Effectively, there are no carbon memory as there is in combustion. These results were obtained during the round robin study for EPA method 415.3 that I showed previously. OI Analytical is very active with EPA and other regulatory agencies for these types of studies in the development of different TOC techniques. At low TOC concentration techniques like heated Prosulfate, these are the techniques of choice. We are often asked how our instrument does at low levels. We believe that heated Prosulfate analyzers are the technique of choice for low-level TOC. We realize that competitive oxidation techniques make the same claim. However, since heated Prosulfate is applicable to other matrices besides only clean waters, we believe it is more valuable to you. And this is just some of the representative data that's capable on a heated Prosulfate system. Particular attention in good laboratory practices, of course, must be employed to avoid contamination of all glassware. Operating parameters should be set for the optimization of TIC removal. Other parameters can be adjusted to optimize the oxidation of the difficult to oxidize compounds in salt matrices. However, these latter two are considered the primary interferences of this technique. The heated Prosulfate technique is applicable to a wide variety of sample matrices. It offers detection limits that are considerably lower than combustion TOC, as well as significantly better precision and accuracy for low-level TOC samples. The challenges that are inherent to combustion technique are not an issue with the heated Prosulfate technique. And then once again, back to our timeline, we'll come over to the development of UV Prosulfate technique. The first UV Prosulfate system was a continuous flow system developed by Earhart. Similar systems are still in use today, although some systems do utilize batch sampling, much like heated Prosulfate technique. Current systems utilize both NDIR and conductivity detection. And for the sake of simplicity, I'll just use the reaction vessel diagram that I used for our heated Prosulfate technique to simulate what UV Prosulfate does. In this illustration, the heater assembly would be replaced by an in situ UV lamp assembly. Elements of this design may be similar to this illustration in regard to sample and reagent injection, as well as moisture removal. In some cases, TIC removal may be accomplished in a separate vessel and transferred to the UV reaction chamber. So both instruments work similarly. In one, we replace the heater with some source of UV light. In regard to interferences, some of the same considerations from the heated Prosulfate technique are applicable to the UV Prosulfate technique. However, there is one factor to consider. Unlike heated Prosulfate, in which heat through convection in the sample reacts with the reagent, UV light must penetrate the sample for complete reaction with the reagent. Turbid samples may prevent complete transmission of light through the sample, thereby reducing the oxidation capacity. Salt-containing samples will react with Prosulfate in this technique in much the same way as they react with Prosulfate in the heated Prosulfate technique. These are just some of the characteristics of the UV Prosulfate technique. Again, these are not my opinion. These are facts that are taken from the relevant methods that govern the UV Prosulfate technique. While the technique may have a narrower dynamic range, good precision and accuracy can be achieved with this technique. Of course, UV lamps do have finite lifetime, and in some cases can be rather expensive. Now that we have these various techniques for oxidation of a sample, the carbon dioxide that is generated must be detected and quantified. In today's instruments, there are basically three choices: non-dispersive infrared, conductivity, or membrane conductivity. Very simply, non-dispersive infrared detectors utilize IR radiation to detect the presence of carbon dioxide. The IR beam is transferred through a chamber while the carbon dioxide in the carrier gas stream flows through it. The carbon dioxide measurement is a function of the absorption of this infrared light in accordance with Beer's law as it travels through the flow cell. Concentration measurements are based on the difference in the IR absorption between a reference and analyte signal. Reference and analyte sample channels measure carbon dioxide in a single path through the use of a narrow band optical filters with appropriately selected bands. Concentration of carbon dioxide present in the optical path will result in a reduction of IR intensity through the flow cell. This slide shows a basic flow path through a UV Prosulfate membrane conductivity detector system. As alluded to earlier in the presentation, some techniques must use the TOC by subtraction methodology for TOC determination, This is one such technique. The basic mechanisms for TIC removal by acidification and oxidation of organics with UV light and its Prosulfate are the same in other techniques. What is different is that each reaction step has its own conductivity detector. The carbon dioxide generated in the oxidation step changes the conductivity of the deionized water. The change in conductivity is related to the carbon concentration in the oxidized sample. The membrane in the membrane module is a CO2 selective fluoropolymer that is hydrophobic and non-porous. The relationship between the conductivity measurement and the carbon concentration is described by a set of chemometric equations for chemical equilibrium of carbon dioxide, bicarbonate ion, and hydrogen ion, and the relationship between the ionic concentrations and conductivity. So there are some assumptions that are made with valid TOC calculations, namely that the pH is predictable and that the ionic species, bicarbonate ion, hydrogen ion, are the only ionic species. These, excuse me just a second. There we go. This technique shares many of the attributes as well as the difficulties associated with other techniques that I have discussed in this presentation. This technique is particularly well suited for high purity or ultra pure waters with relatively low TOC concentrations. Samples with a high degree of dissolved CO2 would be particularly problematic, as well as samples with particulates or high turbidity samples. The potential for positive interferences due to membrane crossover must also be considered with this type of instrumentation. So in conclusion, there are three techniques that are available today: high temperature combustion oxidation, heated Prosulfate with NDIR detection, and UV Prosulfate with either NDIR or conductivity. All the techniques are adequately governed by regulatory methods. The regulatory methods should be reviewed for guidance on which TOC technique is most appropriate for your application. No single technique is optimal for every application. However, operational parameters can be adjusted so results meet the criteria of a particular regulatory method or bring results within the error of the measurement of the method. The ultimate choice of a technique may be dictated by ease of use, cost of ownership, or standard operating procedures in your particular laboratory. And with that, looks like I stayed pretty much on time, and I believe we'll have a short session with questions and hopefully some answers. And
John,
I thank you. Yes, Michael.
thank you. Sorry to jump in. Thank you very much for that truly educational presentation. That was full on. That's 69 slides, but all the attendees remained online and are still here. So that's just fantastic. And thank you once again for your time. And as John said, we are now going to open it up to some Q&A, some questions and answers. We do have a few minutes left. Just a reminder that you can simply type out your question into the chat question box on your screen. Have no fear if we run out of time and can't cover your question. Any questions you do add to the box will be followed up by John offline. He'll reach out to you. The way GoToWebinar works is that all of your questions are automatically tagged with your email address. So John will know exactly who asked the question and can follow up with you. So John, let's start with the first question. There's actually quite a few of them. You're a popular guy. Which carrier gas do you recommend with this instrument, with the TOC instrument?
Depending on which instrument we're talking about, if it's a combustion system, and then once again, depending on the nature of the sample, either oxygen or air can be used. With a heated Prosulfate instrument, ours in particular, which does use a carrier gas, nitrogen, air, which is carbon dioxide free, or oxygen could be used. We do have one customer in Australia, I should mention, who has used argon as a carrier gas, but that is truly an exception. So the heated Prosulfate instrument has a little bit more latitude in the selection of gas. Combustion TOC, of course, must use some type of gas where you have a fairly high content of oxygen, which is used in the oxidation of the sample.
Great, John. Thank you for that. Another great question's just come in. With so many merits with TOC, in your opinion, is it possible that TOC will replace COD or BOD for routine monitoring of effluent organic pollution in, let's say, 5 to 10 years?
I would say it's going to probably happen faster than that. I can speak from our experience in the United States in that the way it works in the United States, that each state in the United States is responsible for all of the regulatory methods that must be complied to as governed by US EPA. And each state is allowed the latitude, if you will, to replace BOD. COD is not used widely in the United States. BOD is the permit requirement measurement. And some states, and I have worked with a number of them, who have replaced TOC or replaced BOD with TOC. Now it does require a rather extensive correlation study. And again, that can vary from state to state. But I am seeing around the world that there is a movement away, particularly from COD. Sometimes there could be toxic chemicals that are used in that measurement. You remove the dichromate. And particularly with BOD, because it affords, the TOC measurement affords a much quicker sample analysis time. If you think about a BOD measurement, it's a 5-day test. By the time you've probably got your samples analyzed, the water that was flowing through your plant has probably gone out to the community and come back around to the front of the plant again. So TOC does offer a quick and easy analysis for TOC compared to BOD. I do see that happening. I do see it happening more and more. It's happening more and more in our country, and I hear that it's happening more and more in other countries around the world.
Thanks, John. Next question. Can ocean water be analyzed without dilution?
Yes. Typical seawater, which has a salt concentration on average in the range of 3 to 3.5%. There are some exceptions where it can go up to as high as 4%, some in places in the Middle East. But those can be analyzed without dilution. in some instances, even higher salt concentrations can be done, but I would recommend when we start moving away from typical seawater levels of salt, that dilution would be easier on the instrument. There have to be some instrumental concerns with using very, very high salt concentrations. As a matter of fact, that's the whole subject of salt and TOC determination in salt samples is another webinar topic I have, and maybe, Michael, that might be the next one we do. I think we should do that.
That would be fantastic. Be happy to support that. Let's wrap up with one final question, John. It's fantastic. All the attendees are still here. They are still listening to your answers. Are there any new products coming in the future that we can look forward to from OI Analytical, perhaps TOC associated?
Well, that's a tricky question, Michael, because I don't want to let too many cats out of the bag at this moment. Suffice it to say that OI Analytical and OI Analytical Engineering is always active in the development and release of new products, whether that be TOC products or products for determination of other compounds of interest, depending on the application. That while one may not be imminent in regard to laboratory TOC, I can say that yes, we're always trying to be at the forefront of releasing new and innovative products.
Great, John. Looking forward to those. We've run out of time, but I'd just like to assure our audience that there is a follow-up email that will be generated directly by GoToWebinar in approximately 30 minutes or so. That will include both a link to this recording so you can view on demand. There's also a link to a certificate, so any of you who did register will be provided with a certificate should you need one. In addition, there's a link to our website webinar page with more very educational and exciting webinars that you can register for or view on demand if it was previously recorded. John, again, thank you so much for your time, sir. And
thank you very much, Michael, for organizing this. It's been my pleasure.
Great. We look forward to hosting another webinar with you soon.
Yep, I would look forward to that as well. So everyone on the call today, I thank you for your attendance, and I look forward to another presentation sometime in the very near future.
Great. Thank you, everyone. Be safe.
All right. Be safe out there.